Dear audience, my name is Duan, and the title of this work I'm presenting is the Security Analysis of Networks. This work was conducted in collaboration with Duan and Chunfujia. We would also like to extend our gratitude to our colleague Dr. Yan Jia for assisting us in presenting this work at I2E Security and Privacy 2024 conference. In this video, we will provide a further explanation of our work. First, let's briefly introduce the difference between the conventional password vault schemes and the honey vault schemes to ease the burden of memorizing multiple passwords. Password vault schemes, also called password managers, are widely recommended by both academia and industry. Typically, password vault scheme stores the vault files on the server. The vault files contain the user's frequently used passwords and related information, for example, the domain names and the username. In conventional password vault schemes, a round-trip decryption will result in the random chunk. This random chunk allows the attackers to verify the correctness of the password master password offline guessing without any external assistance. Therefore, conventional password vault schemes are vulnerable to offline password guessing attacks. While the honey vault scheme is built on the honey encryption scheme, round-trip decryption naturally yields semantically meaningful decoy words or passwords, thereby fooling offline password guessing attackers. The core of the honey vault scheme is the honey encryption scheme. Honey encryption is a type of symmetric encryption application. It includes a distribution transformation encoder and a conventional symmetric encryption scheme. Honey encryption is particularly suitable for scenarios with low entropy keys and messages. DTE is a pair of encoding and decoding algorithms. During encryption, DTE encodes the message into a fixed-length binary code, and the symmetric encryption scheme encrypts the code to get the ciphertext. The decryption process is the reverse. The honey property is that when an attacker inputs the wrong key, K star, the decryption yields another code, S star, which is decoded into another legitimate message, thus fooling the attacker. Message recovery security is a crucial security property of the honey encryption scheme. In the MR game, a user randomly picks a message and a key. Honey encryption then honey encrypts the message to get the ciphertext. Then the user sends the ciphertext to the MR adversary. The goal of the MR adversary is to guess the challenge message, that is the user message, successfully. At Eurocrypt 14, Jules and Respond used the hybrid argument technique to derive an upper bound on the MR advantage, which is a valuable result. But this upper bound cannot model real-world attackers. To address this issue, we utilize the Bayesian posterior estimation method to construct the theoretical optimal attacks against the MR game. Refer to the theorems 1 and 2 in this work. Our attack strategy is to enumerate all low-entropy messages, rank the messages based on the Bayesian estimation, and guess in descending order of posterior probability. This is a very useful attack strategy that can get honey vault distinguished attackers. Next, we analyze the security of the DTE in the honey encryption scheme. As previously mentioned, DTE is an algorithm pair, including a randomization encode algorithm and a deterministic decoding algorithm. A secure DTE must satisfy the correctness of encode then decode, and the indistinguishability between the distribution of binary codes obtained by randomly picking a message then applying DTE, and the uniform random distribution over binary codes. At Eurocrypt 14, Jules and Respond first construct the generic DTE using the inverse sampling technique, that is the ISDT. ISDT first determines the cumulation distribution interval where the message lies, and converts this interval into a set of uniformity points through the representation function, with each point corresponding to a binary code. The DTE randomly selects one point as the code of the message. The figure below shows the illustration of the DTE. The blue interval is the real message distribution, while the red interval is the distribution of binary codes. It's also modeling the decoy message distribution of the DTE. To prove the pseudo-randomness of the SDT, traditional proof techniques typically measure the statistic distance of single core response distribution in two systems and sum them, while our work improves the existing proof techniques by using the k-squared divergence to measure the upper bound of the statistical distance of Q-core response joint distributions, yielding much tighter results. The new result allows us to reduce the code length of ISDT without weakening the system's security. Next, we analyze the message recovery security and known message attack, that is MRKMA security. The only difference between the MRKMA game and the MR game is that the MRKMA adversary has access to a private encryption oracle. At Eurocrypt 4.16, Jaeger et al. Presented the following result. Let K be the low entropy K space. When the MRKMA adversary's current number is log of K, the MR advantage is at least 1 over 2 kappa squared. The kappa squared is equal to the log of K. This result, although valuable, but it does not describe the global picture of the MRKMA advantage. To depict the global picture of the MRKMA advantage, our attack strategy is for the MRKMA advantage to first obtain Q plaintext ciphertext pairs by querying the encryption oracle, then enumerate all low entropy keys to decrypt the Q ciphertext, and compare the decrypted plaintext with the original plaintext to filter out some invalid keys. We call the remaining unfiltered case the consistent case. Note that the real user's key must exist in the consistent key set. Using the random oracle assumption in the MRKMA game, we direct the factor 1 at factor 2. Factor 1 describes the upper bound on the probability that a key is a consistent key, and the factor 2 describes the upper bound on the probability that at most one key is a consistent key. Combining factor 1 and 2, and we obtain the lower bound on the probability that only the user's real key exists, which is our result. We verified this with a real password dataset, RockU, showing the advantage of our results. Additionally, we further improved the Jaeger et al.'s proof techniques. The improved techniques also can describe the global picture of MRKMA advantage and provide the lower bounds on the advantage in the message recovery security with set information, that is MRSI security. Now we move to the security analysis of Honeywood's scheme. The core of the Honeywood scheme is a natural language encoder, NLE, which includes a password probability model (PPM) and a set of distribution transformation encoders. During the encoding process, PPM first passes the password into a rule set. The DT encodes this rule set into binary codes. Essentially, the security of the Honeywood scheme depends on the design of the NLE. Our security model is captured in this slide. We model the attacker as the Honeywood distinguisher attacker. The goal of the Honeywood distinguisher attacker is to distinguish the unique real word from the impossible looking word. Our proposed attacks mainly include the super-encoding attack and the theoretical grounded attack. The super-encoding attack builds on the Tenet or the encoding attack framework and further considers the non-uniformity of the charged DT's code probabilities. The theoretical grounded attack is an instantiation of the optimal attack strategy we previously proposed for the MR game, including some reasonable computational simplification. The evaluated Honeywood schemes mainly including NoCrack and Golan NLE. In summary, the evaluating results demonstrate that an improved success rate ranging from 1.15 to 4.35 times compared to existing attacks. Finally, we selected a security discussion focusing on how to design secure honey vault games based on previous secret analysis. It includes the three design principles that and that's the end of our work. Thanks for your attention.